All right, so last week or 2 weeks ago, I recorded this lecture. I'm not going to spend a long time explaining it again. We have to move to something else, so I'm going to recall the main points. I hope you have been able to watch the recorded lecture. If you haven't been able to do it, and if you follow what I'm going to present, it should be enough for today, for the content of this new lecture. So we started cooperative games. So it's completely different with the previous 3 chapters. Now players can cooperate. And we have to find a model for this. And I think a better name for this course, not only game theory, but it's a kind of modelization. Try to find a description of some interactions. And what is the idea about cooperative games? So we still consider n players. We keep this capital N for the players 1 up to n. But now we are going to consider subset. So for example, if we take just the number 1 and 2, so if S is just 1 and 2, it means 1 and 2 can do something together. This is called a coalition. So S, any subset of this is a coalition. And with this notation, I just count how many elements are inside S. So it means the number of players in one coalition. So if I take just 1 and 2, this S would be 2 in this case. So the number of players would be 2. Of course, if the number of players is 0, it means S is the empty set, which is included in this. And if S is n, it means we take all players. So we are going to use this notion of coalition. It's important. And then I introduce this R power S. So this is the same S. And what does it mean? You're probably not familiar with this notation. You are more familiar with R power small n. But here the meaning is slightly different. R power S means the variable xi, xj, xk, all belonging to R. So you take all real numbers. But I, j, k are in S. So if I take again 1 and 2 and I put R power the set 1, 2, it means I consider only the first coordinate x1, the second coordinate x2, that's it. So be careful, it's really only the coordinates which are in S. And it's a real vector space of dimension, exactly this number. And I also introduce a partial order on this set. We say that x is smaller or equal to y if each coordinate of x is smaller than each coordinate of y. So it means if xi is smaller or equal to yi for all I in this set, if I consider x and y in Rs. And then I introduce the notion of comprehensive set, and I encourage you to draw some pictures. And I put just 3 dots or 4 dots in R2. This is not a comprehensive set because the notion of comprehensive set means you take all values which are smaller. So here we would have to take, if I do it in, let's say, in Zn because it's slightly simpler, but I have to take all entries or all points in Z2 which have coordinates which are smaller. If you do it in R2, you would have something of this type. You take, because here we have coordinates which are smaller than these 2 points or 3 points and this one. So comprehensive set is essentially a set which is big on the left or going down. Think about it. It plays an important role. And then I just introduce quickly NTU games, which are non-transferable utility games. However, the problem is that this is a very general set of games, but they are defined by 2 elements. N, the set of n players, and V. So V is a function defined on all subset. Remember, this means all subset of n. So for example, the set 1, 2, or the set 1, 2, 3, or the set 1, 4, 5, and so on. So these are subset of n. And so you associate to every subset of N a subset of Rs. So, for example, such a set in Rs. So this is the definition of a NTU game. And you have also some conditions which I do not recall. But what is the idea? The idea is each point, for each coordinate, this is a utility or the value that one player can get. So for example, if I take one point in R2, it means the first player is going to get a certain value x1 and the second player a certain value x2. So for each coalition, for each S, you give a subset of possible allocations for the player in this coalition. So all the values they can get. And by the way, you observe that I put N, capital N, it's the same as Rn. This is a set of all allocations, so all possible values that the N players can get. But now, of course, we need to find, or I define what means feasible allocation. I don't want to recall it. It's a bit subtle, so you have to be careful. But as I said, it's natural. It's a way to distribute the utilities among the players, but we cannot say so much because the framework is too general. So that's why then we move to subfamilies of gain. But the idea is really with this subset of Rn, we provide all possible gain or payoff for each player according to the coalition they belong to. All right. And then I introduce the notion of bargaining problem. These are defined just by two quantities, but in fact, they also belong to the NTU games. But it's much simpler because you only have one subset of Rn, which is called the feasible set. So only one of them, you don't have this complicated structure. And you have what is called the disagreement point. So it's also a point in Rn. It's what the player would get if they don't agree. And then you introduce Fd. Let me just say it. Fd is everything in F which is bigger than D. So for example, if D is here, Fd would be this part of my picture. This would be Fd. These are all points which are bigger than D. D is this yellow point, and still in F. Okay. So bargaining, but again, we don't have the structure of all these possible S. It's just one set and one disagreement point. And I introduced it's called Pareto dominated, but in fact, it's simply this notion of bigger, but probably there is some historical reason why it's called Pareto, which is the name of a person. And for this game, there is one thing we can do is find one rule so this is a set of all these bargaining games or bargaining problems. Find one way, one rule which send any of these games to one point in Rn, which would be how you allocate the utility to all players. And the statement, the final statement, if there exists a unique way to distribute these payoff among all players, which satisfy 4 conditions. But there is a unique solution for all these bargaining problems, and this is why it's simpler, because we have a clear solution. There is one way to distribute the utility or the gain among all players according, or if this way follows, follows 4 conditions. And I don't want to recall now these 4 conditions, but just very shortly. Symmetric is if at the beginning all the players cannot be differentiated, then you are going to give the same amount to everybody. This is fair. If you cannot distinguish them, then at the beginning, then you cannot distinguish them when you give the money or the outcome. Efficient means there is not a better way to distribute the money. So all players will be happy because there will be not a better solution. This CAT means we have seen that the utility is unique. It was probably in the first chapter, is unique up to a affine transformation. So it simply says that this function is also independent of the choice of this affine transformation. So this is a small, slightly technical, but it makes the theory consistent. And the last one, which is apparently the most controversial one, means if you have two games and one is a subgame of the other one, but still the solution of the smallest one, no, the solution of the biggest one is inside the smallest one, then it is also the solution of the smallest one. So there is a precise statement. And it turns out that we can even give a formula for this phi. It's the Nash solution. It's in terms of a argmax. I introduced the notion of argmax of a certain function. So you define a certain function on FD. So you define a certain function on FD, and you check where this function takes its maximum value. It's a unique point, and it is the solution of these games. So it's very quick, but this is what I recorded and what you should have seen 2 weeks ago. So it means I introduce very general games, NTU games. They are too general to find something interesting, but then we studied one subfamily, and for this subfamily, there is one unique way to provide the outcome or the utility to all players, which satisfies these 4 conditions. Okay. So today we are going to see another family of games. Here it was non-transferable, so it means a player could not give anything to somebody else. Now the new family, it's called transferable games, precisely because inside a coalition, player can share the outcome. So the outcome of one coalition is important because it can then be distributed among the player in the coalition. So this is section 5.3. It's called transferable utility games, or simply TU games. And so the main difference is again that a certain quantity can be distributed among a coalition. So we consider that N is a set of players. And I'm going to consider a subset and S inside N. This is just an introduction. I will give a precise definition of TU games right after, but I want to tell you what makes it different. So if we consider an NTU game, so if I consider is an NTU game, I can consider the following quantity. Small v of S, it is the maximum over all x inside v of S of the sum of xj. And I sum j belonging to S. So what is this quantity? We take a coalition, S is a coalition. I take all points which correspond to the outcome that this coalition can get, and I check on these points I take the sum of what each player can get, and I take the maximum. So it's the maximum value that one coalition can get, and this number is given by the sum of what each player in the coalition can get. It's a natural definition. So it means because they can share the money, so now it's meaningful to have this quantity. So this is called, it's called the worth of the coalition S. And because of this quantity, more precisely, this quantity is going to be the main one for a TU game. So now I define precisely what is a TU game, but I wanted to emphasize what is new compared to the general NTU games. So I give you a definition. A TU game, so for transferable utility, it's again two things, N and V. But what is V? So this, we know this is a set of N players. There is no difference. But V is from 2N to R. So for each subset of N, I associate a number with a certain condition. It satisfies that V of the empty set is 0, which is, okay, just a normalization. And this V is called the character. In fact, if you open any book in mathematics, you can always find a characteristic function for almost every subject. But in this case, it's called the characteristic function of the game. But in a different subject, it would mean something completely different. And the set of all TU games is a GM. So a TU game or transferable game, we have just N and one function from this set to R. So it's rather simple compared to the definition of an NTU game. But now I'm claiming that a TU game is in fact part of an NTU game. So the claim, which is easy, so we just look at it, claim is that the TU games are inside a bigger set, which is NTU, which is not clearly visible because they were not defined like this. So it means I need to do something to see a TU game inside the NTU. So how we see it, for any S inside N, S different from the empty set, we set V of S. So I start with this object, but I define a capital V of S. It's a set of X in Rs such that the sum of I in S of its I is smaller. What is this object? If you have done calculus 2, you should see what it is. We are in Rs and we have one condition. So it's a half space. If I do it in R2, it would be something like this half space, because you have, or maybe, yeah, you have one condition. I don't know if it looked like this, but it would be half of a space for sure. Just think about it. So for each, so this small v of S is given by this quantity. And I define capital V of S with this inequality. And I also define V of empty set is just the point 0. This is a definition. And then small exercise for first-year student. If you just look at the definition, this N and this family of subset is a NTU game. Why it's not so difficult? Because you just have to check that with V given by this, the conditions of an NTU game are satisfied. I didn't check, but it should be easy. Or I don't. Yeah, okay. It's a half space inside RS, not inside Rn. To think about it, yes, but I wrote in RS. I encourage, again, it's partially your job just to look on any reference book or anywhere on internet to find some examples. If I spend time on examples, it takes half of my time. And then I have no time to build the theory. So this is a personal choice. I prefer to give you the main definitions and trying to explain you the main definition, and I don't spend so much time on examples. But yeah, this is your job to, okay, look for one simple example to really understand what is the meaning of all these things. And I give some indication in the notes. So again, a TU game is this and a function from the subset of N to R, but it defines, any TU game defines an NTU game, which is more complicated, but it's given by this definition. Now we have another definition, which is quite nice and quite simple. These are some properties. Oh no, not properties, let's say additional properties of TU games. Additional properties. Why additional is important? Because it's some additional property that we require. It's not automatic. So let NV be a TU game. The first property, which is the strongest one, we say that NV is super additive. Additive. And it's a natural property. If for any subset S and T in N with an empty intersection, we have V of S union T bigger or equal to V of S plus V. What does it mean? I'm claiming that, and it's a definition. We say that it's super additive if the value that the union, the bigger coalition given by S union T is bigger than the sum of the two coalitions. That's the meaning. So a group of students could get this amount, another group could get this amount, but now if they go together, they can get a number which is bigger. This is a notion of super additive. This is quite natural. So some games have these properties, some do not have, of course. I'm not claiming that all games have this, but it's a possible property that some games can have. It's a rather long definition. So this is the strongest property. Now we say that NV is weakly. It's a bit strange. It's called weakly super additive. weakly superadditive. If for any, you take now just one player and you take S inside N minus this player, so all other players except this one, and you impose that V of S union I is bigger or equal to V of S plus V of I. So you can see it's slightly weaker than this one, because this one for any coalitions, this is only a coalition with one more guy. So a coalition with one more person has an outcome which is bigger than the initial outcome of this coalition plus the individual outcome. Okay, and this is weakly superadditive, and it is additive if we have an equality, if equality only. So I put two definition in one. It's weakly superadditive if we have an inequality or equal, and it's called additive if you only have one equality. Now, a third property, which is also natural, NV is monotonic. And be careful. I'm quite confident that if you work a bit, you can see that these notions are not equivalent. You can find examples where one is satisfied and not the other one, or vice versa. So it's monotonic if whenever you have two coalitions with one included in the other one, which one S is, so it means you take a subfamily of players, then the V of the bigger family is bigger than the outcome of the smaller family. So this is monotonic, so the more members you have, the bigger outcome. Again, be careful, it's not equivalent to this one. Yeah. Of course, you can, at the beginning, the definition of an NTU game is almost nothing. There is no constraint. But now in practice, you should think like this. In practice, whenever you want to model something, these definitions are quite natural. But I could put an inequality. Yeah, the more people, the less money you have. This is also true. So depending on what you do, but so I'm just saying, these definitions are quite natural in a certain context. I'm not saying that you cannot do something else. And and again, it's your job to find some examples which naturally fit in this framework. And finally, NV is called zero normalized. And again, this is quite natural. If V of any individual player is 0. So it means if one player alone can only get 0. This is zero normalized. And then there is just a remark about this superadditivity. It's in the notes, I will not write it. But observe that if anytime you increase the size, you have either the same amount or something bigger. What is the natural thing which is going to happen? You will just get all players here, which is called the grand coalition. I introduced it last week or 2 weeks ago. So maybe I can write if superadditive the grand coalition, so when you put all players together, will likely appear. Again, it's not a clear statement because if you have equalities and not inequalities or equal, there is no reason to work together. But if you have some inequality, some strict inequalities, probably you will get the grand coalition. And I remind you that the grand coalition is capital N, which is one subset of N. So these are 4 possible additional properties for a TU game. Still, on this blackboard, we don't see how to choose any allocation. So we will need some criteria for distributing the money or distributing the utility among the player. This is one solution is in the next section. But before this, I just want to state an exercise for second year. So for any TU game, I'm going to so I define a new TU game, NV, with a 0 here. And how I define V0 of S, it is V of S, which is defined here, minus the sum over I belonging to S of V of I. So what does this represent? It's an amount, or I speak about money, but of course it can be anything, but the worth of a coalition minus what each player in the coalition could get individually. So we subtract what they can have without participating to this coalition. So I define it. The first thing to show is that this NV0 is a TU game. And the second observation or exercise to do is that this NV0 it's still there, it's 0 normalized. This is quite easy to see. Normalized by construction, it's 0 normalized. And the third thing is the initial game is weakly superadditive. The one property, if and only if, when I put IFF means if and only if, so you have to show in 2 directions, if and only if this NV0 is monotonic. So how to show this? You start with NV, you construct this. This is not just by definition. Then you check what means superadditive, and you check that if NV is superadditive, then this new game is monotonic. And then the next thing you do is you assume that this one is monotonic, and you check that it implies that the initial one is weakly superadditive. So you have to show something in 2 directions. But as I just said before, so far I haven't given any what is called allocation rules. So there is no reason to choose any way or any specific point inside Rn, how to distribute the worth. So we will do it in this next section and in the next one. So now, just before the title of the section, we need what this is called either solutions or allocations rule. which means choosing some x in Rn, and x in Rn indicate what each player get. So choosing x in Rn, which is acceptable for all players. Of course, this notion of acceptable is not defined yet. And it depends what we want to do. So, and the next section is one solution for this. And it's called 5.4, the core. This is the name of the main object. We will see. So this is one answer for this problem, and it will become more clear. So first of all, for a TU game, the TU game is always this n and small v. An allocation x in Rn. Of course, I use both notation. I remind you, these two things are the same. R with a capital N or R with a small n, it's the same, simply because we are dealing with n players. So for any TU game, an allocation is efficient. Probably it helps for understanding. It's efficient if the sum of xj, any j, is equal to v of n. So what does it mean? This v of n is given in the definition of the game, because this v, remember, this v is a function from 2n to r. So you associate to any subset of n, and in particular to n, a real number. And we say that it is efficient if, when you take what each player get, so the value of xj for the sum of xj for all j, you get Vn. We say that it's efficient. Again, in the general, if you take an arbitrary, or if you define V arbitrarily, this is not so meaningful. But now if you think about the definition I gave before about monotonic or about superadditive, this is usually not for arbitrary game, but this quantity is usually the bigger one. If you think about monotonic, it means whenever you take a bigger set, the value is increasing. So if the game is monotonic, this Vn is a bigger value. Or if it is superadditive, it's also the biggest one. Okay? So we say that it's efficient if, it's a definition, if the sum of xj is Vn. So now I just make one more sentence. If V is superadditive, and many games are superadditive apparently. Thus, if NV. Oh, by the way, I've seen some author forget the n, because V is always defined on 2 power n, so this information is not really useful. If I just give you V defined from Rn power Rn to R, you don't need this information, but I try to keep it. So if NV is superadditive, X in Rn is just a remark, is efficient if the worth of the grand coalition, which is N, is distributed among all players. Why I mentioned this? Simply, if it is super additive, as I already mentioned, the grand coalition, which is N, is likely to take place. And then it's, I mean, this, what is there means simply that the value of the worth of this grand coalition is going to be distributed among all players if it is efficient. But now we have individuals. So each individual do not want to lose money or to get less than if they don't play. So this is a first observation or a first remark. The allocation X in Rn is individually rational, it's individually rational. We have already seen this notion of rational a long time ago. It's individually rational if xi is bigger or equal to v of I. What does it mean? Yeah, no, it's individually rational if, so x is, a point in Rn is individually rational if the value for the player I is better than what the player I could get without doing anything. V of xi is what you get if you don't participate to any coalition or you just stay by alone. Is individual for any I in this is a quite natural requirement. So according to this, I define a first set of allocation. So given a game NV, we define, I don't know what, I don't fully understand this word, the set of imputations. So if somebody can explain me the meaning of this, I would be happy, the set of imputations. So I give you the definition, but I don't fully understand the meaning. It's called I of V. I is for imputation, and V is because we are dealing with a game. It's a set of points in Rn so that there are two conditions. First, the sum of I xi is Vfn. So it means x is efficient and it's individually rational, which means that the condition I have just written before, xi is bigger or equal to v of I. So this is what is called the set of imputation. So the set of x in Rn such that what all players can get together is equal to Vn. But in addition, each player gets more than what they would get without playing. So it's a natural set. And why is it natural? Because individually, you have no interest of not choosing a point in this set. Look, think about it. Individually, no interest of not choosing a point in I of V. Because no matter which point it is, you get more than if you don't do anything, right? So this is already a good set in the sense that all players would individually, if you're alone, you would say, okay, this is better than if I do nothing. But it doesn't mean that if you collaborate with somebody, you're happy with this set. Because it might be that some point, if you decide to collaborate, it might be that some of these points are not good. Or some points are better than others. So this set is, as it is written, individually, no interest of not choosing a point in S, but coalitions, or some coalitions, might not be interested in all points of I of V. Why? Because, you know, we have different points, different way to distribute the money or the outcome. You are not sure that if you don't play with somebody else, you cannot get for some points more than for other points. There is no condition of this type. So it means we need to find a better definition in order to satisfy all possible coalitions. I told you, if you think about it, it's a quite nice approach. So we need to do something better. Because coalitions are possible, we need to refine this notion. And how do we refine it? The second definition. So it's even, again, given envy. This was a set of imputations. Now I define the core. So the core is defined by, it's a set of, and it's denoted by CV, the core of V. So it's a set of X in I of X. So it's a I of V. It's a subset of this one, but with one more condition, so that the sum of I in S of xi is bigger or equal to V. And what does it mean? It means that no matter which coalition you do, so a coalition is a subset of S, no matter which coalition you do, you look for the points where the sum inside the coalition is bigger than the max you can obtain for this coalition, or what this coalition is possible to give you. So look, it's a subset of the set of imputations, because now we impose that all possible coalition will be satisfied with this point. So now it's a remark, no coalitions has interest of not choosing a point in C of V. So please check that you fully understand this sentence, why this is true. Because if you do a coalition, so if we play together, the money we can get together is bigger than this amount which is allocated to coalition. So it means these point X are the best one, because no matter which coalition you create, you cannot get more. So it means this set is really the interesting one, because you cannot, no matter how you collaborate, you cannot do better. So if we understand this set, or if we can describe this set, we have the best solution for these games. So you can wonder, oh, how can I describe this set, or what are the properties of the points in this set? Because they are, and by the way, if you take S, just check, if you take S just 1 point, you still have this condition. Oh no, this condition here. If you take just 1 point, so this is more general than this one, because it's for any coalition, and this is just for the coalition of one player. So the Kerr are really the best solution you can look for. But there is a natural question. Given a game NV, does a Kerr exist? If it doesn't exist, then it means you cannot look for the best solution. So I will finish this lecture by giving a if and only if condition about the existence of a Kerr. And now, still another question. If X belongs to a Kerr, so we have seen that it has some very interesting properties, does it possess additional properties? And the answer is yes, and we will see it in a second. So once you have that this Kerr is the best solution for all possible coalitions, you can wonder what are the properties of these solutions. So in order to describe additional properties, I need to introduce one more definition. By the way, if you have any question, please ask. Not only Hevidu, but all of you can ask questions. When I had no student, when I was recording, it was very painful not to have any interaction. There was an empty room, and it's very annoying. So please ask questions. Hevidu, any question? So it means it's understandable. Good. Or not at all. Okay. I want to define additional properties. So let NV. My sentences are always the same. Let NV be a TU game. Okay. And I consider S a subset of N. S different from the anti-set. Take for X and Y in this set of imputations, we say that Y dominates X through S. This is a new notion. It dominates X through S if first the sum of I in S of Yi. So what does it mean? So we take two solutions which are individually rational because they are in the set of imputations, but we say that Y dominate X if this first condition is something we have already seen, it means that y is in the set, sorry, it's smaller or equal. It means that y is in the set V of capital S. Remember, at the very beginning of TU game, I said a TU game also define a NTU game, and it was exactly this condition. And for all coordinates in S, xi is smaller than yi. So it means if x, or no, I mean, this is a definition. It means that y dominate x through, oh, I forgot, through S. Y dominate x through the subset Fs if y is in this set. This is not a big problem, but we have this. And now, still in this definition, or separately, it doesn't matter. You can do it in the same definition. We say white dominates X without adding through S. We say that Y dominates X if there exists a S inside N so that Y dominates X through S. So please observe that this is more general because I say Y dominates X if there exists a S. In the first part of the definition, I fix the S. Now I let S any coalition. So Y dominates X if there exists a coalition such that the previous statement holds. And you can still do it in the same definition. X is undominated if there is no Y, there is no Y in this imputation set which dominates X. So this definition contains three statements. What means Y dominate X through a given coalition? Then what means Y dominate X? But it means there exists a coalition where you have the first part of the definition. And the third one is X is undominated if there is no Y which dominates X. So my aim was to give additional properties. So now let me state additional properties of the curve. It's a proposition. For PU game NV, the first statement is if X is in the curve, then X is undominated, which is good because it means you cannot find a better Y no matter which coalition you generate. And the second point is if the game is super additive. So far, I didn't use this assumption. If the game is super additive, then C of V, the curve is a set of X in a set of imputation so that X is undominated. Please again, think carefully about the difference between these two statements. The first one, I have no special additional condition on the game. I'm just saying if X is in the Ker, it has an additional property, which I introduced. It means X is undominated. So it means the element of the Ker is defined in a certain way, but they have in addition a certain property. Then the second statement is if the game has this addition property of being super additive, then the elements of the Ker are all the elements in the set of imputation which are undominated. The proof is not so difficult. If somebody wants to look at this, it's possible. You had a question?
I'm not so sure, but if X and Y are both in the set of imputations,
Yeah.
That just means that they are better than strategies where one player plays by themselves, right?
Individually.
Yeah. Okay, that's it.
Yeah, there is a definition for the set of imputation. It's the sum is V of n, and individually they are rational. But I could probably state this definition even without being in the set of imputation. Okay, so keep in mind we have a definition of the Ker, and it turns out that the elements of the Ker have an additional property, and this additional property is even sufficient if the game is super additive. Again, I encourage you to look at examples. I'm just going to add one more sentence, but there are pictures in the book I'm using, but also in many other books. And I will not spend so much time on this. It turned out that I and the IV and C of V, so the set of imputation on the Ker, are bounded convex, what is called polytopes. I decided not to give the precise definition. I gave the link to Wikipedia. But what it is, remember, I mentioned half space, half planes, or half space. So this is a very simple polytope. But if I cut it in any way by another plane, it's still a polytope. So polytope is a convex polytope is like this. It's a convex set, but where each face is flat. Of course, you have to be a bit more precise, but it is the intersection of half space. So each surface is given by, in this case, a surface. So this is a notion of convex polytope. They can be infinity. They can be infinite. I mean, if you continue in both directions, it would still be a convex polytope, but it's not bounded. But in our case, if you check carefully the definition, they are bounded. So you can see in the book some pictures representing this set inside Rn. So if you're interested in geometrical features, you can check the definition of this and check why these two sets are of this type. However, they can be empty, which is a little bit annoying because I told you this is the most interesting set because it shares many properties. If it is empty, then it's a bit annoying, but this happened. Okay, the simplest example. I decided to speak about this simplest example for one reason you will see in a second. So I need to give a definition of the simple example, which are called simple games. So NV is simple. This is a definition. Again, the word simple appears in all topics of mathematics, always with a different meaning. but in this framework, a game is simple if it is monotonic. Monotonic means whenever you take a bigger number of players, the worth is increasing. So it is monotonic, and it takes value only in two sets. Oh, sorry, in two numbers, 0 and 1. So the value of a coalition, the worth of a coalition is only 0 and 1, with V of n equal to 1. And this is true for any S. So it means this is a very simple game because each coalition takes only two values, 0 or 1. And monotonic means if you have certain number of players and if you add, the worth is increasing. But increasing means since you go only from 0 to 1, if you're already at 1, adding more players, you are still at 1. So it means these are very simply defined in the following sense. If I give you, these games are observation. Because they are monotonic and take only values in 0 and 1, they are completely defined. By what is called the winning coalitions. What are the winning coalitions? It's a set of S in N such that V of S is 1. If I give you this information, you know that all the other one takes the value 0. And you can even take the set of minimal coalitions because of this monotonic property. If I give you only the minimum one where it's 1, for all bigger, it can only be 1. So these are easily described. But I like the next definition. What is a veto player? In fact, this is the reason why I'm giving you this example. It's a very simple but nice definition for NV simple. A player I is a veto player. And I'm sure you have some example in mind. Is a veto player if V of the grand coalition minus I is 0. So as soon as one player does not participate to the grand coalition, the outcome is 0. This is the definition of a veto player. And think about the United Nations. You have this kind of rules. As soon as one member decides not to be in favor of something, there is no decision. And the next proposition is, for me, slightly a mystery. So I would be happy if somebody works on this next proposition. It's not difficult. The proof is not long. So but I don't fully understand, or I don't have a clear idea in mind. For NV, a simple game, a simple TU game. So I would be happy if somebody decide to work on this. The curve is not empty if and only if, so it's if and only if again, there exists at least one veto player, at least one. And there is even, it's stronger than this because there is a description of the curve. And in this case, So if there is a veto player, in this case, we can describe C of V. The Kerr is given by the set of X in a set of imputations such that Xi is equal to 0 for any non-veto player, So I would be happy if somebody look at the proof. It's not very long, so it shouldn't be difficult. And we are only dealing with 0 and 1, so you have only 2 alternatives. But I would be also happy if somebody give an example. What does it mean, or what can you illustrate this with already 3 players? You can probably do it. So one possible report. I linked to one example also for this. Okay, what is the last thing I want to present? I said the Kerr is the most important thing, because if you know the Kerr, you have the set of points for which no coalition would object. They are the best for all coalition. Can we have a statement that it exists if and only if something else? We are always happy if we can describe with the if and only. And the answer is yes, but I need to introduce just a few more things. This part is not essential, but I still like it. But it's not essential. If you cannot completely follow, it's fine. First, the first definition is not difficult. The restriction for NV, so a TU game, and a subset N in S, the restriction of this NV to S is, I will explain, SVS with Vs of T is equal to V. Think about, you have 5 players and suddenly you want to restrict to 4 players. Then how you change your game? So you start with n players. Now you want to restrict to a certain number of players. So I can define the restricted game with precisely this restricted number of players. I need to define this new function. And how I define it, for all t now which are in S, I just take the previous value. So I eliminate, if I eliminate one player, I eliminate all sets which contain this additional player. So this is called the restriction. You start with a game, let's say, with 5 players. You want to consider only the first 4 players. So you define the game with 4 players, and this function defined by simply taking the value of the initial game, but for all sets which are made of only these 4 players. So, okay, so this is not difficult, but I will need it in a few minutes. You remember when we were dealing with strategic game, we defined first pure strategies, but then also mixed strategies. Mixed strategies is you take part of pure strategies, half of half, for example, or probability distribution among pure strategies. So here we are going to do the same. Instead of just being in one coalition, you can say I'm half in one coalition and half in another one. You can interpret this in terms of probability. You take the 50% of probability to be in one coalition, 15 to be in another one, or you spend, depending on what you do, half of your time you are in one coalition and half of the time you are in a different coalition. So this is what I'm now going to introduce. I need to describe this notion. But if you have in mind mixed strategies, you can understand it. So a family, curly F, inside 2n minus this antiset. So what does it mean? It's not completely trivial. Let's say you have two players. With two players, you have different sets. You have this set, you have this set, you have this set of three players, and you have the set of first player and third player. Okay. Now I take a family of this. So for example, I take these three elements. So F is made of three subset of n. You choose some of them. So family F of subset is balanced. This is a new word, is balanced if there exist numbers. So positive real numbers. And I'm going to denote them by alpha S for S, a subset in F. It should be coherent. So I will finish the definition and then we will understand. There is a family of numbers such that so the sum over S F so I've never written something like this. What is the meaning? Yes, it looks strange, but it's not. I said I took these three. In this three set, two of them contain the point 1. So I'm summing over all, and this is for all I. Among this family, I sum the set of F, which contain 1 point, the point I. And I want this sum to be 1. Why? Because each player is going to be distributed into 2 or more coalitions. But altogether, the probability of one player to be in 1, 2, or 3 coalition is 1. It has to end up with 1. Or the time spent between coalition 1 and coalition 2 has to be 1 for all players. So I sum over all sets in my family so that I is in S. So I do this sum. Then if I take the player 2, I would have to sum again. I would have to sum over 3 sets because 2 is in these 3 sets. And for the player 3, I would have to sum over these 2 sets. So I sum over the set of the family which contain I. Okay? So this is called a balance, and it's not easy to satisfy this condition. It's not easy to find a family and some constant between 0 and 1 so that it sums up to 1. But I give you an example of a balanced set of balanced family. F is a partition of n with alpha of S equal to 1 for any S. So if I take again my 3 points, a partition, remember, is, for example, these 2 points on this one. Then you can check, and you put alpha S is equal to 1. Because it's a partition, each sum will be made of only 1 term, and you have it. So a partition is an example. But again, the idea behind this is now we are going to distribute each player among different coalitions. Do you have a question about this definition? Try to have an example in mind. If you have this example in mind, you can reconstruct the definition. So this is a notion of a balanced family. You are able, within this family, to distribute each player among different coalitions, but the sum of the time, the total time for each player is 1, or the total probability for each player to be distributed among all subset is also 1. And now the main definition for this last part, this was a balanced family, but now a TU game. NV is balanced. So now I say this for TU game, it's balanced if for any balanced family of coalitions, because all these are coalitions, one has a sum balance family capital F should give an. So what is the meaning? The sum of all S in this family of alpha S Vs is smaller than Pn. What is the meaning? It means no matter how, you are now allowed to be divided into different coalitions. So half of you can be in one coalition, half of you can be in another one. You do all possible distributions. So you do with a balanced family, you look, now if you are in two coalitions, half of you is in two coalitions, then you get half of the money in one coalition and half in the other one. So this is precisely the gain, the probability times the worth of each coalition. So this condition tells you no matter how you distribute yourself among different coalitions, you cannot get more than the worth of the grand coalition. It's a condition, it's a definition. We say it's balanced if no matter how you get distributed between the different coalitions and how many time you spend in each coalition, you cannot get more than the grand coalition. And sorry, we sum, over. I hope in my notes it's F, or did I, is it F? S in F, is it?
Yes.
Okay, because what I have written here is not correct. And there is again this interpretation about this in the notes. And what is the main statement? The main statement is that there exists a curve if and only if the game is balanced. This is a rather deep theorem. It says NV has a non-empty curve if and only if NV is balanced. So I wanted to finish with this. The proof of this is not trivial. It's a rather complicated proof. But it precisely says we are interested in situation when we have a non-empty curve, because again, this is the best solution because all coalitions would be satisfied with elements in the curve. But we have a characterization of game with a non-empty curve with a different condition. I'm not claiming that this new condition is easier to check, but it's still a if and only if. You are happy when you have two solutions for checking something. And this condition, once you understand what is the meaning of this balanced family, you can be distributed among different coalitions. Then this is called the aggregated sum, or the aggregated payoff, because you take from each coalition according to the time or according to the probability you spend in each coalition, but the total aggregated payoff cannot be bigger than this Vn. And if this condition hold, then the curve is not empty. And there is one more point in the definition about totally balanced, but I don't need to introduce it for now. Okay. So we have seen today, and if we summarize what we have seen, the first part was a definition of a TU game. So a game where the notion, this V plays a role because you can share the worth of a coalition. And so I introduced the notion of superadditive, weakly superadditive, monotonic, and so on. And then we introduce the notion of curve because this is the best allocation you can get, or each coalition can get. So the notion of curve is individuals and arbitrary coalitions are happy with the solution contained in a curve. And they are undominated, so you cannot get a better solution than something which is in a curve. By the way, it doesn't mean a curve contains only one point. Be careful about this. You can easily construct sets which correspond to elements in a curve, and none is bigger than the other one. For example, if we have a game with two persons, one get 2, I get 1, or I get 2 and the other one get 1, none of them is better. You can simply not, if you have to choose between 2, 1 and 1, 2, none of them is better than the other one, but you have 2 solutions for this game. So a curve, it doesn't mean that there is only one point. But so if you want to distinguish points in a curve, you need now an additional condition that I gain more than what the other one can get, or something like this. But I don't know. This is a good question because it was for simpler game. If you look at bargaining problems, there were not coalitions. In bargaining problem, it was much simpler. You had no, the subsets were not apparent. They did not appear. So I don't know if you can, this is a good question, if you can implement this notion of symmetry, efficiency. Efficiency, yes, it is efficient because it corresponds to undominated. But the notion of symmetry, yes, I don't know if we can implement it. Probably. Or the 2 other conditions, yeah, we have to think about them. Maybe inside the curve, yes, there are points which satisfy an additional property. That's possible. Yeah. But it depends on the game. Okay, so that's all for today. There are 3 more lectures. Next week, it's normal. The next, so on 16, we are going to take a picture. So I encourage you to come on the 16 if you want to be on the picture. And if you are online, I will add you. There is a way to add you. I did it in the past. And on the 23, I will do one more lecture. I said it's not, you are free to come or not, but I will try to speak about something slightly different. So it's also of interest if you can. Okay. And if somebody